I'm going counterclockwise and I have a current coming out, right? So, what if I have more than one current? Well, you can apply the result for each current, and you end up with the following. So, here's what I mean. I'm saying here, what if I have a loop and we got some currents going in and some currents coming out, like this. Okay? And maybe a current that's outside, that's not within the loop. So, it says the following, Ampere's law. Just like, it would remind you of Gauss's law. It says the integral of v dot ds over a closed loop is equal to mu naught times all the currents that go through that loop. So the little subscript. Sometimes some books use enclosed or currents through and so on. Now I need to also tell you that when you sum up the currents, if you're going counterclockwise, the currents that come out, they're counted as positive. The currents that go in, they will count as negative. Because they're, you see, a current out contributes a counterclockwise magnetic field. But a current into the board will give you a magnetic field in one direction, clockwise. So that dot product will be negative, right? Because phi is this way, but the magnetic field is this way, so they make 180, so their dot product is negative. So how do you count currents? If your integral is counterclockwise, the current that comes out is positive, and the current that goes in is negative. Let's do a conceptual question, and then we will do some calculations. Here is a conceptual question. Let's see. Suppose, for example, so this is Ampere's law. Example. Suppose the integral of v dot ds is equal to 7 mu naught. And here is what you have. You have here's your loop. Here is I2. It's coming out. Here is I1. It's equal to 6 amps. And it is going in. I2, let's say, is 8 amps. And the question is, here is I3, but it's unlabeled. It's not out, it's not in, you don't know. And we would like to figure it out. We want to know if it's going in or going out, and how much is it. Okay? So Ampere's law says the integral of v dot ds is equal to mu naught times the current that goes through your loop. The currents that go through our loop are 2 and 3, right? I2 and I3. I1 is not relevant because it's outside the loop, right? I1 is outside the loop. So we get the left-hand side of Ampere's law is v dot ds, but we already know that they're telling me it's equal to 7 mu naught. So I got 7 mu naught on the left-hand side. On the right-hand side, I have mu naught times the currents that go through the loop. One of them is I2. The other one is I3. And that's it. I don't have, I1 is not going through. So cancel mu naught. So you got 7 will equal to I2. Should I count it as positive or negative?
Positive.
Positive, because I'm going counterclockwise and it's coming out. So I2 is 8 plus I3. So I3, therefore, will equal to minus 1 ampere. So in what direction is I3?
Into.
Into. Because its magnitude is 1. It's 1 ampere, but its direction is into the board. Okay. One more. here is another example. So, let's say I have I1, and then I have I2. The question is, find d dot ds. What would this integral give you in terms of I1 and I2? Apply Ampere's law. Let's see. B dot ds will equal to mu naught times the currents that are enclosed, right? So what are they? What currents are in my loop?
I1 minus I2.
Yeah, I1 is coming out. I2 is going. Yeah, 2. I2 is going in. Yeah, that's the answer. Coming out, I2 is going in. Yeah.
What's the reason again why like the outside currents don't contribute to it? Is it just because we've like defined it that way, or like?
You can prove it. I didn't want to go, but.
Oh, is it complicated? I'm sorry.
So you got that? No, that's okay. I would just sketch it through. So let's say here is let's say your current is here, all right? So my current is here, right? And my loop is here. And I want to do B dot ds. You see, if you do B dot ds, as you integrate, there will be a magnetic field due to this loop, right? But as you integrate, the angle is trapped between this and this. It will increase, and then when on your way down, you don't really loop through 2 pi. You will come back, so the integral just give you 0.
Oh, okay.
Yeah. So, but I would save it for another time, maybe. Yeah, so the current that's outside, just like Gauss's law, the charges outside of the surface would be 0. And yeah. Anyway.
And the for Gauss's law, it'd be a similar proof.
For Gauss's law, I forgot how we proved it in the case of Gauss's law. I think it was similar, yeah. I think it's a similar proof, but it's not a line integral, it's a surface integral.
Right.
Okay, it's a surface integral. So I wanted to just mention 4 things that we have learned so far. 4 things, or maybe 3. Here are they. Well, speaking of Gauss's law, here is the one we learned. E dot dA. Yeah, speaking of Gauss's law, what was it? E dot dA. Q enclosed or Q within the thing, right? Qn over epsilon naught. Good. We also learned E dot dL or ds. I think dL or ds. Ds it was?
DS.
ds? Okay. E dot ds over a closed loop. What was it? If it's a closed loop. We did all our circuits because of that.
0.
0. Yes. So 0, right? When you go around the loop, it's a conservative field, so you get 0. Yeah. This is the electrostatic field, right? So, yeah. And now, today, we learned the following. First, I will write the B dot dA, leave it blank, and then B dot ds. This one was mu naught I, right? I through. How about this one? So think about the flux lines. If you have any magnetic, any closed loop, do we have any, like, can you enclose just the north pole by itself?
No.
You cannot, yeah. So you always have a dipole. You always have a dipole. So the magnetic field, if you draw any surface, any surface, the magnetic fields, there will be magnetic fields coming out, but then there will be just as many coming in. So your surface integral of E dot dA will always give you what?
Zero.
Will always give you zero. See this one, because you have actual charges, it's related to the charge. But here, we don't have magnetic monopoles. So this will always be zero, at least up to now. Yeah. Okay, so we have four equations. We will modify them a little bit when we get to Faraday's law. These are called Maxwell's equations. So we have four. Okay. I want to do two more examples, and hopefully I get through them. I wanted to get through the forces also, but let's see. So the first example is that I'm going to do. Suppose I want to calculate the magnetic field for a current carrying wire that is not really thin, but it's actually thick, like a cable. And I want to figure out what the magnetic field is inside the wire and outside. Okay, so if I can erase this one, these two boards, these two, I want to erase them, and then I will get. So I want a cable that has a certain radius, and the question is, what's the magnetic field inside the cable, and then what is the magnetic field outside of the cable? Outside, it's a cable, so it's an infinitely long wire basically, and it will look like mu naught I over 2 pi r. That's what it would be. But inside, that's a problem that we will use Ampere's law to figure it out. So let me show you why we would want to use Ampere's law, not the messy Biot-Savart law. So I could erase this, no objection. So, so here's a cable. The cable is of radius some capital R, right? Some capital R. And it's carrying a current. And the current, let's say, is in this direction, current I. So, question is, what's the magnetic field inside? What's the magnetic field outside? And the current is long. I mean, the wire is long. So you can take it to be infinitely long. So, on the outside, in what direction will the magnetic field be? Can the magnetic field have some kind of an angle like this? No. By symmetry, it will either has to loop around, or it has to kind of just diverge outwards. It doesn't diverge outward because we don't have those sources, we don't have those monopoles. That's one way to think about it. Another way is, if you reverse the current, the arrows have to go in, but if I take the entire wire, just flip it physically, the arrows don't flip in. So that's a contradiction, so it can't be going outside. Anyways, it will loop. They will loop around. Just as an intuition, magnetic fields, they always loop. Electric fields, they go away. Electrostatic fields, they go away. They diverge. So, I'm going to grab. So the current is going like this, right? Actually, I take it back. Let me make my current this way so that Gauss's Coulomb, Ampere's law, I don't have to deal with a minus sign. That's all. So let me make my current go this way. And I'm going to draw a loop. It's called just like Gauss's law, a Gaussian surface. This one would be called an Amperian loop. So an Amperian loop of radius little r. This is the loop. And my loop, I will go through it this way. That's why I wanted my current to go this way, so I don't have to deal with a minus sign. So the current is coming out of my loop, and then my magnetic field will be looping this way, right? So the question is, what is the magnetic field? Now, if you try to apply Biot-Savart law, see, this is a thin cable, so you have to apply it to every single piece, starting at the center and going off center and doing all these cross products. And it's going to be a mess. And after you finish all that mess, you will get the simple result that Ampere's law will give you. And so here's what we will write. So you got B dot ds, just like Gauss's law, U naught times the current that's through. We have to talk our way out of many things until we just get one number. So we're going to talk our way out of the dot product first. ds, by symmetry, first of all, here's the current. I said the magnetic field will be looping this way in the same direction as ds. So since they are parallel to each other, the magnetic field and ds, they are parallel to each other, it means B dot ds will be what? Will just be B times ds, right? Because they're parallel to each other. Their dot product just goes away, and it will just be the magnitude of the first vector times the magnitude of the second vector, times the cosine of 0 degree, which is 1. So this left side, you would have just B times ds. Okay? That's what you have on the left side, because they're parallel. B and ds are parallel. On the right hand side, I have mu naught times the current through, the current that leaves. I don't have the entire current out. I have just a portion of it, this portion, right? If I draw my loop around the entire wire, then yeah, the current through will be this whole I. But I don't have the entire I. What do I have? How much of it? Well, it's, yeah. So the current density will be the current divided by pi capital R squared, but the area that I have is not the entire area, just pi little r squared. So it will look like this. The current divided by the entire area, which is pi times capital R squared, times the area that my loop encloses, which is only pi little r squared. So that's the proportion I have. So how much area do I have? Does my loop cover? Only pi little r squared, but the current, the entire thing, if I want to enclose it, I have to make a radius as big as this one. Okay. So that's what I have. Yeah.
So is the current, like inside the wire, is it just a radius of big R?
The current, yeah. So there is current throughout the wire. So the current is running throughout the wire. So, but the ones outside of my loop, they don't count. Only the ones that go through my loop count. And the question is, in proportion to capital I, how much current do I have?
Is this wire hollow or is it like in?
No,
it's not, right?
it's not hollow. Yeah.
But that whole like circle is all the current will flow through that whole circle.
Yes.
Okay.
Yes.
That makes sense.
Yeah. So the current is flowing this
But
way.
but we only care about little r.
Only the little r. Yeah. So that's the proportion that we have. That's the proportion. So the pi cancels. Now B dot ds, B, as long as I'm at the same radius, right? As long as I'm at the same distance away, it will be the same magnitude. So B is constant, as long as r, little r is the same. So now what's the closed integral? So I would have this, B, closed integral of B, of just ds is equal to mu naught I, little r squared divided by capital R squared. What's the integral of ds? It's the entire yeah, it's the circumference. ds is the segments, so it would be 2 pi r, yes. Yeah. So this part would be 2 pi r. Remember what ds is? It's the arc length. It's this arc length plus the one next to it, plus the one next to it, plus the one next to it. When you add them all together, you get the circumference. So it's 2 pi r. So b times 2 pi little r is equal to mu naught capital I little r squared divided by capital R squared. You can cancel this one and this one, and you end up with B will be mu naught I over 2 pi capital R squared times little r. So this is the magnetic field when little r is less or equal to capital R. Okay. Magnetic field. Now, when you go outside, when little r is greater than capital R, it just becomes like a wire. So it just be, so for, and B would be equal to mu naught I over 2 pi little r, or little r greater than capital R. Because then it's just a wire carrying a current. Yeah.
So the left is like the only solve for is basically like the magnetic field of like a cylinder like radius r inside the wire.
Yeah, you can think of it as a cylinder, yeah.
Okay.
The wire is cylindrical, definitely, yeah.
For B, is it lowercase or is it uppercase or?
For outside, so if you're here, if you're a distance, if you're here, then it will be lowercase r.
Okay.
When you're outside. So, the next one is the solenoid. It requires a little care, so we will do that. There is an important result that I want to show you for the solenoid. So hopefully you follow the arguments, but at the end there is one result that I want to emphasize. It's a simple result. Basically, the magnetic field inside the solenoid will be a constant, and it's equal to something. And we want to figure that out. So, this is, by the way, it's an example from in the textbook the author does. So solenoid. Solenoid looks like it's always hard to yeah. Yeah. Right. By the way, I disclaimer, you should look at nicer pictures in the book. So it's supposed to be a wire that is wrapped and it goes up, right? A coil is just wrapped on top of itself, right? Like that. It doesn't go up, it doesn't snap. So the way you can think of a solenoid is like a loop on top of a loop, 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 and then they're just stacked this way. They're just stacked. Okay? So the current is going like this. So if you look here, the current is coming out, here it's going in. Coming out, going in. Coming out, going in. So the current is going like that. It's looping. So it goes in on this end, it comes out. It goes in and it comes out. That's the current. Let me slice the solenoid this way and look at it from that perspective. We're going to slice it. Not a real slice, because if you cut it with scissors, then you have no current, right? You cut your wires. So it's just an imaginary slice. So we're going to cut it. So here's what you have. So this loop that comes out, this one comes in. So the current here is coming out. The current here goes in. Comes out, goes in. Comes out, goes in. Goes in. Comes out, goes in. Goes in. Comes out, and then goes in. All right, that's enough. And the solenoid we will consider is an ideal solenoid. By ideal, it means they're stacked together very tightly, and the solenoid is infinitely long. Of course, there is no infinitely long solenoid, but this much solenoid is considered infinite enough. Even if it's this much, it's infinite enough, and it does the job. Okay. So that is our solenoid. So the loops are like this, right? That's you see that? Right. So we're just looking at this. first claim is that the magnetic field outside is zero. The magnetic field inside will be parallel to the axis, and it's just straight up. And then outside of this region, it's also zero. Okay? So let's see why that is. So first, do we agree that the magnetic field on the outside has to either be parallel or this way maybe, and then it's and then we would figure out why it has to be zero. Do we agree that? So first of all, let's say you're looking at this one here. The current is going in. So what kind of magnetic field will it produce next adjacent to itself? If it were to produce one, they will end up canceling. So the claim is that the magnetic field has to either be this way or this one of them. Yeah, it's probably this one when you're near this one. Okay. But from farther away, that will end up canceling from farther loops, because it's the magnetic field of a loop as you go away from it. It's not the perfect circle. It's non-uniform. I have it. I erased it. It's not the perfect circle. So the claim, first of all, it's either down or up if there is any. Okay, either up or down if there is any. Yeah.
Wait, this in and out current, that's you're describing the solenoid thing.
That's the solenoid. Yeah.
Okay, all right.
Yeah. It's going like that.
Going down to the outside, right? For that one, it's going.
Yeah, if you're for just this one, yeah, it would produce a magnetic field down. But then the other ones, because of the non-uniform field, they end up. Some of them are actually up, and they will cancel.
So,
Yeah.
if you look at right now, you say on the right side it goes down, right?
Well, on the right side of just this one.
So how about on the left side, does it go up?
On this side?
Oh no, like in the middle.
Here?
Yeah.
Yeah, it will go up. Yeah, in the middle it will, yes, in the middle definitely up. So all I need you to agree with is that the magnetic field here is either down or up. Those are the two options. Okay. Let's assume it's down. Okay, let's assume it's down, and then we will figure why it has to be zero. So here is the argument. Can I erase this one? It's not really useful. You know what we're going to use? Ampere's law. And we're going to draw our Amperian loop like so. This, and then this. This is my Amperian loop. Let's call this one here 1, 2, 3, segment 1, segment 2, segment 3, segment 4. So, and the length of the segment, the length from here to here, let's call it L. The length of the segment is 1. So outside of the solenoid, so outside, B dot ds over closed loop is equal to U naught times the current through. You can apply Ampere's law anywhere you like. I'm just applying it outside. Now outside, what's the current through that loop?
Zero.
No current, zero. Yeah, there is no current that is through our loop, so zero. And so this right-hand side is zero. Now, you know from Gauss's law, the right-hand side being zero doesn't mean the magnetic field or the electric field from Gauss's law is actually zero at all points. It just means this integral ends up being zero. So let's see how we can show that it's actually the magnetic field that has to be zero. So I'm going to divide my integral into 4 integrals, because the loop consists of 4 portions. 1, 2, 3, 4. Here are they, or here they are. So you would have B dot ds over the first portion, over path 1, plus the integral of B dot ds over the second portion of the loop, plus B dot ds over the third portion plus B dot ds over the fourth part of the loop equal to 0, the right hand side is 0. Now, B we said is either up or down. Let's look at portion 2. ds is this way. The magnetic field is either down or up. So what's their dot product? 0, they're perpendicular, right? The magnetic field we agreed, it's maybe down, maybe up. But the ds is this way here. And in part 4, ds is this way. So they're perpendicular. So that means this one is 0, and this one is 0 because of the dot product. They're 0 because of the dot product. The next portion is, or let's look at 1. Let's assume, for argument's sake, without any loss of generality, we'll just say magnetic field is down. Let's say there is a magnetic field and it's down. So B dot ds in this case, they are parallel to each other, right? B and ds, they are parallel to each other, so it just becomes B times ds. So this one would just become the integral over portion 1 of B times ds, that's all. And then, for this portion, so if the magnetic field is down, and ds is this way, right? We're going around the loop. So ds is this way, B is this way, so their dot product will be negative, yeah. So it will be negative, so it will be minus the integral over the third part, B times ds equals to 0. And so for this one, at part 1, I'm going to call it B1, B at that position, and then B2, B3 at this position, right? So I'm saying maybe the magnetic field here is different than here. Maybe they are different. So, but as long as I'm the same distance away from the loop, as long as I'm the same distance away, the magnetic field should have the same value, whatever it is. So so it will be B1 throughout here, and it would be B3 throughout here, right? Because it's the same distance. So this one would just be B1 times the integral of ds. The integral of ds is the length of this segment of the loop. What's the length of that segment? It's just L, right? So it's L. And then for this one, it would be B3 times L equals to 0. Now, divide the L out and you get the following. B1 is equal to B3, right? B1 is always equal to B3. So, here's what, yeah.
How is it negative again?
Yeah, so the magnetic field, we said, let's assume it's downward, right? Yeah. So the magnetic field is down, ds is down here, right? So they're parallel. So it would be positive, their dot product would be positive. But here, the magnetic field is down, ds is up, so they make 180.
Oh.
Yeah, and so it would be cosine of 180, which is minus 1, yeah. So I get B1 is equal to B3, no matter how far away. Now let's say I make my loop infinitely far away. What is the magnetic field at infinity?
0.
0. Well, and it has to equal to this one still. So what is B1 then?
0.
0. So if you're outside, it will be 0. A simple explanation is this. You have magnetic field here, and then magnetic field flux wants to get out. But the solenoid is really infinitely long. So it wants to get out, but it gets out at infinity, so that's where it winds down and it comes back. But it's infinitely long, so it never comes back. So there is no magnetic field here. Nothing comes back. So by whatever reason or reasoning, the magnetic field outside is, yeah.
So right now we just did the right side though.
We did the right side, the left side will be the
Yeah,
same.
okay.
Yeah.
Yeah, just make sure.
Because it's symmetric, right? Anywhere you are, whatever it is, it will be the same. Yeah. So now we need to argue inside. Inside, the argument is this: the magnetic field has to be constant inside. It has to be constant, and it's how you argue about it. I'm just going to do it kind of quick. Here is my loop. My loop will be here. Okay, very similar to this loop, but I'm now inside. So, in this portion, what is B dot ds? 0, because the magnetic field is up, right? So B dot ds here is 0, and B dot ds here is 0. In here would just be, it would be B times ds, right? In here would be negative B times ds. And what is the current enclosed within this loop, or the current through? 0. So we would have a similar equation as B1 equals to B3, like we had earlier, except now the magnetic field is not 0, and so B1 will just equal to B3. So it will have a single value inside here, and it will be up. That is it. So it's just B inside. So now what is it? How much is it? See, we argued our way out of the field here. We said it's 0. Now we argued our way here. We said, okay, it must have one value. It must have a constant value. It's upward. Now let's see what that constant value is. Now you do your Amperian loop. Draw your Amperian loop, and I will draw it slightly longer. So here is my loop. My loop, and it will go like this. So let's argue for that one. So you have on the outside here, let's name them. 1, 2, 3, and 4. Okay? 1, 2, 3, 4. So inside, so the integral of B dot ds over 1 plus the integral of B dot ds over portion 2. B dot ds plus B dot ds over portion 3 plus B dot ds over portion 4. So let's see what they are each. B dot ds at this place, what would it be?
Negative.
We're outside, so what's the magnetic field? 0. We're outside, so this portion, the magnetic field is 0, yeah?
But, like, you said magnetic field is going down, right? So isn't it same direction here?
Outside?
Yeah.
Well, we said, let's assume it's going down, but then we argued it's 0. We said, if it's there, let's say it's going either down or up. And now we argued that it has to
It
be
is
0,
zero.
so it is 0 on the outside.
Oh,
Yeah. So with the loop here, with this loop, this portion of the loop is outside. So B dot dl will be, or B dot ds is, it's 0 because the magnetic field itself is 0. How about B dot ds over this portion?
0.
It's 0 because
90 degrees.
it's at 90 degrees. If you're light outside, it's, it's still 0, and then here it would be 90, so it's 0. So this one is 0 because the field itself is 0. This one is, maybe it's perpendicular, or it is still 0 if you're slightly outside. If you're here, it is something, but we will deal with this one in a second. If you're here now, what is the magnetic field, or what is the dot product?
0.
It is 0 because it's perpendicular again. So this one is 0. For this one, we said magnetic field is pointing up, ds is pointing up, so their dot product is just B times ds. So let's look at that portion. So you got B